Alright, today we're going to work with area, and that's theorem 6.1. If you want to read over this for a minute and write it down, I should have a copy of this PDF for you, so you won't have to take as much time drawing the graphs. But basically, we've been dealing with area of a given function, let's say the blue one, and the x-axis before. Well, today we're going to look at given two functions, say our y equals f of x function, and given a second function, y equals g of x, being able to find the area in an interval a to b of this highlighted region. And that's just real simple. We'll take the area of this f of x, which would be all of here, and subtract out the area of the g of x function, and that would give us our highlighted. So we're going to look at that. These are some terms that you might see. Our upper boundary, we want to take the upper boundary and subtract the lower boundary. Okay, and we have a corollary. This is just, remember this looks familiar to our Riemann sums format of taking the limit, and then now it's rewritten in the definition we were given just a minute ago. So this is considered your limit of sums, your length of your rectangle, and the width of the rectangle. So just to see that and remind ourselves of what exactly these different forms look like. Okay, so the first thing we're going to talk about is an Rx region. Basically, it's going to be our integration with respect to x. So we have a given function, f of x. This is our upper boundary. A given function, g of x. And we want to use a dx width. So basically, it's the width of rectangle, a vertical rectangle with width dx. And we're going to talk about this a little bit more. But on this next screen, I have guidelines written down for finding area of a Rx region. So if you would pause it and write this down or print out the PDF. The first thing we'll do is we'll sketch the region, label the upper and lower boundaries, find the smallest value x equals a and the largest value x equals b for our points. So in terms of x. Then we're going to sketch a vertical rectangle and label it dx because it's going to be for our Rx region. Then we'll express the area of the rectangle as our f of x minus g of x and apply the limit of sums operator and evaluate the integral. So pause this and jot this down. And then our first example is going to be to set up an integral that can be used to find the area of the shaded region. Now I sketched this out for you already. Sometimes they'll just give you these and you can either use your graphing calculator to make a sketch, or you can make an XY table and highlight the region in the middle. So let's look at that, but all we have to do is set up the integral, so we're not necessarily going to evaluate it this time. Okay, this is our formula from the previous page. We're dealing with our Rx regions, which means I'm just going to have a rectangle of width dx. So I'm just going to sketch a vertical rectangle here and label it dx. That's with dx. This is also, I'm going to make a note, we want to solve this in terms of y equals. So if I rewrite this red one, let me do it in red. Rewrite it. Y is equal to, what's that going to give us? Negative x plus 6, right? And we also, the other one's already solved for y equals. The reason why we want to do this is because when we plug in our f of x and g of x, we want them to all be in terms of x because we're taking with respect to dx. So make sure they're all in respect to x. So we take a minute and do that, and now we're going to say, write it in black, area is equal to, okay, on the x values, where is our region, our interval? So it's going to be from what? The x value of 1 to the x value of 4. So that's where your upper and lower. Okay, if I want to make myself a note, this one is considered your upper boundary, and this blue one is your lower boundary. So we want to do the upper boundary minus the lower boundary. So we would write that. The upper one is negative x plus 6 That's this red line. Remember, it's solved for y equals, so it's just negative x plus 6 minus the blue one, which is what? Square root of x dx. Okay, and that's all they ask us to do, to set it up to find the area. We are not going to evaluate this. So a couple of things to remember. If we do a dx, it's a vertical rectangle. We have dx. We remind ourselves that all of our variables in here need to be with respect to x, so they need to be x terms. And then our boundaries are in relationship to the x values, so 1 and 4 are there. Okay, so let's look at an RY region. So now this is integration with respect to y. This is when we're given the x equals g of y function on the left, a x equals f of x function on the right, and our rectangle is a horizontal rectangle that we labeled dy. And then our interval are going to be relationship to the y-axis, so we just called it C and D, so it's just different from A and B. Since we used A and B for our x, we'll do C and D for our y. So this is considered, this blue one would be your right boundary, and the red one we consider our left boundary. Okay, just like last time, I gave you some guidelines for finding an area of Rx, so this is your guidelines for the RY region. If you'll take a few minutes and jot that down and read through that, we'll be able to apply these. But this first particular problem, okay, we're just going to set it up just like we did last time. So I'm just going to try to familiarize you with setting these up before we actually work a lot of these out. So I'll give you a few minutes to sketch this and then we'll get started. Okay, so first I just wrote our formula down. I let this be C and D just because it was defined that way. It really doesn't matter what variables we use here. If we say A and B or C and D, we know that that's our upper and lower limits or our leftmost and rightmost. Okay, so let's write our area in relationship to what we have. So first of all, we want all of our terms to be y terms because it's a dy, so they're solved for x equals, and that's nice because that's already done for us. If these given equations are not solved for x equals, we would have to do that first. So it's nice, that's been done. We can see, let's look at our y value to see that our values will be from -2 to 1. So looking at the y value, you can see right here I have this ordered pair labeled. The y value is -2. Okay, it's hard to see that's highlighted right there because my sketch isn't the greatest. And right here at the y value of 1, because remember we're doing a dy region, and let me do horizontal rectangle and remind myself that, just kind of fill this in. Let's put dy right there. Okay, so these are in respect with our y values. Now we can write our right minus our left. So our rightmost function for our rectangle is going to be the blue one, right? So we want to do the blue one minus the red one. So the blue function is going to be -3y squared plus 4. And the red one is just going to be y cubed. And then we have dy. We just want to make sure that all of these have a y variable, dy, that these are in terms of our y values, and that's going to be it. So I'm going to make a note down at the bottom. I'll say right minus left. So our right boundary minus our left boundary is what we would do here, where in the x one we did the upper boundary minus the lower boundary.